Okay, so lecture 4 or lecture 11, part 3. Okay, and so now we're getting into the independence of working memory and long-term memory. And so the way that you realize that long-term memory and working memory are different is because of a word list free recall test. And the thing that people detected was a recency effect, which reflects working memory. Okay, and this recency effects means that the words that were said to you most recently, you're gonna remember better. And this goes away when you get distracted, and so this recency effects gets abolished. And so if you are distracted, it won't go into your long-term memory. And another thing is that with slower presentation, there's a better recall, and that is linking to long-term memory. And so if you present something slower, then the early words are going to be remembered better because they're going to go into your long-term memory. And the slower presentation does not affect the recency effect because that is a working memory thing. Okay, and then another thing to note is that MTL amnesiacs have the early words for MTL amnesiacs, they don't do well with those. And so that's someone like HM. And so HM isn't going to remember the early words because he doesn't have enough working memory to kind of reach back that far. But in MTL amnesiacs, recency effect is okay. So like if you say to HM, cat, hat, bat, he probably won't remember cat or hat, but he'll remember bat. He won't remember cat because it's too far back and he can't reach into long-term memory, but he will remember bat because it's recent. And so that's the recency effect. Okay. And you can think of this because MTL is for LTM declarative. Okay, and so another main point is that MTL is for LTM, and that the LTM has to be declarative for it to be an MTL. Okay, and so these are anagrams of each other. The MTL is an anagram. Okay, and so another patient study is KF, and you can think of him as KFC, so I just refer to him as KFC from now on. And he was studied by Warrington and Shallis. And so you can remember this as where the shame, where the Shallis, Warrington Shallis. So where the shame, where the Shallis, Warrington Shallis. And you can remember the shameful person wearing a shell in the middle of KFC, which is super funny. Okay, and KFC is the opposite of HM. Okay, and KFC had left temporal parietal cortex damage. And so that's LTPC. So left temporal parietal cortex damage. And so just remember that KFC is not the right way to eat. And so what is it? It's the left. And there's no right time to eat it, or you have to eat it at the right time. Don't eat it late at night so that you sleep and all the fat goes into your system. And so it's the left temporal lobe, and it's in the parietal cortex. So left temporal parietal cortex. You remember parietal because it's KFC, there's chicken, which is kind of like parrots. So left temporal parietal cortex damage was KFC. Okay, and so severe working memory in KFC, working memory in KFC was very bad. And so KFC, basically, he couldn't remember like anything that was just happening. So like if you threw a ball at him and then he looked away, like 2 seconds later he'd look at you and he wouldn't even be mad because he didn't realize that you threw a ball at him or like you hurt him or anything. And so his working memory could only extend to like 2 digits, and there was no recency effect. And so even if you gave him cat, hat, bat, he wouldn't remember anything. He wouldn't even remember bat. Okay, but long-term memory is good. And so if you gave him a long word list, he would do good. And so KFC, you can think of this like really long line into KFC. And yeah, that's always how it is because long-term memory is good for KFC. People always remember to come back to KFC. They always remember they like it. And so that's a long word list. And that is a double disassociation. And so double disassociation means working memory is bad, but long-term memory is good. So that means that you know who you are, you can remember episodes, but you just have nothing to work with. You have no working memory. Okay, and so another way to remember this is KFC makes it bad in the moment because you'll get sick, but long-term you'll have a lot of nutrients and proteins. And so that's just, again, saying like bad working memory in the moment, but long-term KFC is able to remember things. Okay, and so and another way to remember that this is a double disassociation is because when you go to KFC, you eat double the calories at KFC. And so that's double disassociation, double the calories. Okay, so HM, just comparing HM had bad declarative memories, non-declarative was okay, and this is a single dissociation. So HM had a single dissociation. And then we're getting into a new patient, and so the new patient is MS, and MS has damage to the right occipital cortex. And you can remember this because MS, what's that sound like? Multiple sclerosis. And one of the first symptoms of multiple sclerosis is bad eyesight. And so damage to right occipital cortex. And so like the occipital cortex is like right, like it should be intact, like the right occipital cortex, but it's damaged. Okay, and so MS damage to right occipital cortex. And so basically what you can remember about him is that prime word recognition tasks he was bad at, so there was no benefit from like previous priming. And so what that means is that non-declarative memories like priming are bad, but this is different from patients like HM, which are MTL amnesiacs, because MTL amnesiacs would have benefited from previous priming, just like HM can remember kind of details about his wife. And also another thing for MS, multiple sclerosis, explicit recognition tasks are okay, like you're good to go with that. And so declarative memory is good. And so explicit recognition tasks, okay, declarative memory is good. And so that means that like episodic memory, like you can remember, like declarative memory is good. And for MTL amnesiacs, that's not the case. And so MS, to sum it up, right occipital cortex damage, and non-declarative memory is bad for MS. Non-declarative memory bad, declarative memory good. Declarative memory good, and you can think of that as like declarative is something you can see and say something about. And so declarative memory is good, non-declarative is bad in MS. And so just going over ways to remember it. MS, multiple sclerosis, is demyelination, that's basically what this disease is, and one of the first symptoms is a loss of eyesight. MS had damage to the occipital cortex, the right occipital cortex, and it's the opposite of what you think because he had damage to this occipital cortex, but declarative was good. It's like things and episodes you can see, And so, yeah, declarative is good, non-declarative is bad. And so basically, like, priming isn't going to help him with anything. Okay. And so now we're getting into neural imaging and just like a snippet on this. And so neural imaging shows that there are different neural substrates or like different neural regions for working memory versus long-term memory and for declarative versus non-declarative. And so there's a separation between working and long-term, and there's a separation between declarative and non-declarative. But also they share a lot of regions in common, mainly the frontal and parietal lobes for both working memory and long-term memory. And so frontal parietal lobes are kind of in common between working and long-term. And so just think about this. Between working and long-term and declarative and non-declarative, or no, not those ones, just between, across all spans of time, frontal parietal lobes are going to be in both of them, so working and long-term. You can think of this as like an eternal parrot. Like the front of the parrot is just eternally living there. Like you can always see the front of the parrot. I don't know what it is. Maybe it's God. But anyway, frontal parietal lobes work for both working memory and long-term memory. And the last thing to note is that the cellular underpinnings of both working memory and long-term memory are probably the same. Okay, and so now we are getting into consolidation. And so there's two different types of consolidation, long and short term basically, but the first one is synaptic consolidation, and this has to do with gene expression, protein synthesis, and new synaptic growth. And so basically synaptic consolidation is just going to be like molecular things, like genes are expressed, proteins are expressed, kind of like this LTP business, like you're building up new connections basically, and that's going to lead to new synaptic growth, which is like new dendritic spines. And we know this because of the application of a protein synthesis inhibitor. And so basically it's something that blocks the making of proteins, and then after you give this to mice, you give it to mice after they learn something, and so or you give it to them after they've encoded it, you give them this protein synthesis inhibitor, and it shows synaptic consolidation occurs within 1 hour because it's basically blocked in there. And so it's a protein synthesis inhibitor, you give it to them after encoding, and it shows that consolidation occurs with about 1 hour. Okay, and then system consolidation. So system versus synaptic. System is going to be like, you can think of it as kind of like the whole brain because it takes way longer. And so while the previous one was pretty quick, system consolidation is going to take days to years. And this is what we're going to talk about later, but it's an entire shift in brain regions. And example, consolidation, declarative memory. So one of the examples we can go over is consolidation of declarative memories, and basically how you consolidate declarative memories, which again are like episodic, they're like things you can talk about, and declarative also includes semantic information and episodic information, so like facts you know and episodes that you know. Okay, and so this is one of the best documented kind of transfers of regions, and it goes from the MTL to the neocortex. You can think of this as MTL to neocortex, M to N, that's like an alphabetical thing. And so we know this because removal of the in mice, if you remove the hippocampus, memory is impaired only during the first month afterwards. Okay, and so another thing to know about memory is that if you replay it in slow wave sleep, you have to replay it in slow wave sleep when you're like really thinking. It's slow wave. It helps with learning. Okay, and so the sequence of hippocampus plus visual cortex, and so basically what that is that, yeah, okay, and so when you replay memories in slow wave sleep, like when it's slow and you're really thinking, you're going to be replaying sequences of things in the hippocampus, which is like a spatial thing, and the visual cortex. And so you can think about like that famous mouse thing where he's running around, and yeah, he's like running around, but what is happening is that we're replaying like these hippocampal place cells. He's remembering like how he ran around, and you can like reactivate him and make him do that in slow wave sleep. So slow wave sleep is going to replay neurons that are associated with certain things from the hippocampus and visual cortex, and the cells are going to fire in order. And so replay is during sleep, and replay is cued during sleep. You have better recollection when you wake up. So that's pretty good. Okay. And so now we're getting into declarative memory. So again, declarative memory could be episodic or semantic. Okay, and so there's two theories of how these declarative memories consolidate. And so like declarative memories are like things you can like talk about, things that you can say. Okay, so the first one is the standard consolidation theory. And this just says that the hippocampus rapidly learns and then slowly transfers things over to the neocortex. And so hippocampus to neocortex. And this is going to happen in sensory and associative cortex. And then hippocampus is going to be useless. Okay, and so this works as memories are reactivated. And so this can be like sleep and stuff. You can remember this, sleep is pretty standard. And then this reactivation strengthens the neocortical connections. So that's like a Hebbian thing, like LTP. Like you keep stimulating it and these connections keep forming. Okay, and yeah, and so standard hippocampus to neocortex, and this is done by reactivation, and it's standard reactivation. Okay, but some MTL amnesiacs lose all biographical memory. And so this is suggesting that possibly there is an unfeasibly long consolidation time, like maybe 40 years, because that wouldn't make sense, because you can encode these declarative memories, but if they're still in the process of decoding, then that would mean that would make sense that when the MTL amnesiacs couldn't remember episodic memories, but who knows what's true. And so basically standard consolidation theory says that hippocampus learns fast, slowly transfers it over to the neocortex. Okay. And MTL amnesiacs make people think, if you're looking at the standard model, that there's a over 40-year, just like huge consolidation time, which is why when you take out that part that's transferring it over, like everything would be lost. It's kind of like on your computer when you have half of a Word document but you don't have it saved. It's just going to delete the whole thing. Okay, and so the second theory is multiple trace theory, and that is that all episodic but not semantic memories depend on hippocampus. So that means that episodes are going to go through the hippocampus, but not semantic information, like not information like, oh, Bob likes strawberries. But episodic information like, oh yeah, one time me and Bob went to the pumpkin patch, and we got an apple milkshake, and then we went to the carousel, and then we threw a baseball, and like these like sequences of events. But semantic information like, oh, Paris is the capital of France, Seattle is in Washington, New York is fun. Like that semantic information is not going to be going through the hippocampus. And so the hippo basically just wants to watch Netflix all day. And so all the episodes are just going to go flying by in front of him, but he doesn't want to see those facts. And so only episodic go through the hippocampus. Yeah, and so all episodic depend on the hippocampus consolidated or not. Okay, and so basically that is saying that repeated retrievals to additional traces in the MTL. So that's a little unclear, but I have a little T-chart here and I'll explain it to you. Okay, so in both of them, the hippocampus learns fast with one exposure and the neocortex is slow and it needs multiple exposures. In the standard model, all declarative memories, that's going to be episodic and semantic, go to the cortex. And so everything declarative you can like say is going to go to the cortex. But in multiple trace theory, only semantic information is going to go to the cortex because the hippo wants to sit there with all the episodes. He doesn't want the episodes to go away, the episodes of Netflix. And so only semantic is going to go to the cortex where like you process things. So you would need facts there anyway. And then the episodic memory is going to forever depend on the hippocampus, which is part of the MTL. Okay, and in standard, multiple retrieval means strengthen the cortical connections, but in multiple trace theory, and you can think of multiple trace because there's like kind of multiple paths. Like the two paths are, if you're semantic, you can walk on one path, which goes to the cortex because the hippo doesn't want to watch you. And if you're episodic, then you can walk on the other path, which means that you're going to go to, or you're not going to go anywhere. You're just going to walk around the hippocampus because the hippo wants to watch episodes of Netflix. Okay, and so in this multiple trace theory, multiple retrievals of episodic means more hippocampal traces. And so basically in this multiple trace model, like, yeah, these semantic information is going to go to the cortex, and that's going to be great. It's going to walk away. The hippo doesn't want to watch those facts. But if you keep retrieving these episodic memories, if you just keep talking about this trip with Bob to the fucking pumpkin patch, then what's going to happen is that it's just going to encode even more in your hippocampal traces. So the main difference here is that in multiple trace model, which is like the different pathways for semantic and episodic, the episodic memories don't get to leave the hippocampus, whereas in the standard they do. But in multiple trace, that trace or pathway is just going to lead right back to the hippocampus. Episodic cannot escape. The hippo wants to watch Netflix.